it's like send a function that has some content in the time domain, to a form that is in a complex domain in the frequency domain. It's basically moving from time domain to frequency domain. If it's like a some function ut, maybe we say that the Fourier transform in a domain f, this integral of the gt with the complex exponential of this form. So basically, the Laurent transform will move a function that is expressed in a domain, in this case time domain, to a form that is in this case frequency domain. Similar with some function that is in space, for example, x, y. Maybe we can transform this to h uv, and if we think about a two-dimensional Fourier transform, and this will be a double integral of things dx dy. Integral and basic. I think it's alright. It's not too difficult. It was the function multiplied by the complex exponential. And instead of ft, it will be now ux plus vy. That's basically the definition of the Fourier transform in two dimensions. But to be known as a transform, it needs, of course, it goes from one domain to another domain, but it needs something else to be called transform. And it's another important thing, is that you should be able to go back from GF, from this domain, go back to the original domain. That step is important, because you can use, for example, transform this, but eliminate half of the information. That's a transformation, but you are not able to obtain back the GF. In this case, if you get GF, you are able to obtain GT from GF, and that procedure is called the inverse Fourier transform. You can see, right? The GT is an integral GF, something like this, right? So you are able to obtain from GF the GT. So with the Laurent transform, it will be the same. What will be similar? We will be working typically in a domain, spatial domain, xy, and we will move this to a domain called d theta. Of course, we will see what's d and theta in a moment. But just think about another transformation, another way to express some image. And that way to express this transformation should have some benefit. Right? You should have some benefit, some usefulness that can be, some operation that can be done maybe in this domain before getting going back in the inverse process. For example, what's the benefit of calculating the Fourier transform? One thing that can be used or can be done.
You look at two convolutions of the function of that time. You can multiply the frequency.
You can multiply the frequency domain, yeah. That could be. In particular, what would you try to multiply? The frequency domain. But if you have this original function, which function that you have seen until now that can be multiplied the frequency domain? What?
The transfer function.
Transfer function, yeah. But in particular, for example, filters. We have seen that. You remember, no? In the frequency domain, there will be some form. But typically, we need information about some particular area of the frequency domain, not all. So, as your friend said, we can multiply, for example, for a high pass filter in this case. That's the case of the Doppler. In Doppler, we work with some transformation of the slow time domain, but at the end, one step is the well filter that we need to filter out the low frequency signal. No? Or if you want to eliminate noise, maybe in other signals, you will like to multiply by a low pass filter. So in this case, the Fourier transform allows to do this operation to eliminate noise, for example, by multiplying this expression in the frequency domain and working this multiplication in the frequency domain before going back to the time domain. So that way you can filter, for example, some information in the frequency domain. Or do some operations in the frequency domain. And we will see one more time here. This expression of the frequency domain in CT, topic X-ray tomography, we will see that with the technology of the projections that I will explain in one moment about tomography, the information that we will obtain is not in this domain. The information will be in a radon transform domain. That will be the sensors are able to capture. Okay? The acquisition will be signals, information in this domain, not directly in this domain. And then, when many signals are acquired in this domain, radon transform, we apply the inverse radon transform and obtain the image that was or corresponds to this information in the radon transform domain. Okay. Creo que algunas personas más han venido, así que ¿ese código?
2020-1607.
07, ¿no?
Sí. David.
Okay, and then a little bit of motivation or difference between tomography and you can say conventional radiography. What would be the difference between this? For example, this tries to express that this image is a CT tomography, computed tomography of one section of the brain inside the skull, and this also corresponds to that, but with X-ray. X-ray imaging. The traditional X-ray imaging that we have seen, that is like you have some crystal tube that will send some X-rays, and this image is the projection of some volume with illumination and everything that we have seen. And this represents the white, represent that maybe it attenuates more, in the black region it attenuates less. So this is a representation of the brain, but notice that this is a projection in 2 dimensions of a volume of an object, brain that has 3 dimensions. So there are some information that is not possible to see. Compared to this image that is tomography, that is a slice in some part of some part of the brain. So this corresponds to a 2D image and is shown as a 2D image. It's just a slice, a plane. It's basically I don't know, it's like a school. Okay, imagine that we have like a cut around this area, only around this. No, but try to imagine this is in this direction. So it's like a plane, and it will look like that. And one thing that this image try to show is that if we look at this part, we see something different than this side, for example, the left side. It means this 2D image allows us to see something strange in the right side of the brain that is not appearing in the left side. If we see this, it's difficult to see that information because maybe I don't know, for here, maybe the structure was around here, for example. Could be around here. But it's maybe a small volume. But when you do the projection doesn't only touch that volume, that mass, maybe that malignant mass, but will touch everything in that path, even tissues around that mass that are healthy. So the projection of that line where the mass was has not only information of the mass, but information about many things. That means that maybe the contrast in this region is not much different than the intensity in this region. So, but here, when we look only at the slice where the mass was located, we compare to tissue next to that region, in that case, we see more differences or more contrast. Okay. More contrast. For example, numerically, what you can do to calculate the contrast could be subtract the intensity, the value in the pixel between two regions, and divide that by the average. That's one way to do that. In this case of CT, the image intensities were 63 and 35. This more brightness. There are more brightness here than here. So 63 minus 35, 28. In some units, HU, we will see that. What's the meaning of HU? HU are the units of CT. Units of CT that H come from Hounsfield. Units. Where Hounsfield is the name of an important person that worked with this topic early in the beginning of tomography. In a sense, like a Riley, Riley in acoustics. It's a name that appeared many times in acoustics, something like that. Hounsfield was a person that worked a lot with these topics. Okay, so we have 28 difference. And in percentage, if we try to express this in percentage, we just need to divide this by the average of 63 plus 35. This is approximately 98 to or I think here they divided by 98 from 49. So 28 divided by 49, you can get something. 50%. But yeah, around that, no, it's almost 50%. But if we look at the contrast, no, between region of mass in the X-ray and the other region, the intensities are much similar. In this case, the units were 1738 minus 1734 divided by the average, no, it's around less than 1%. Of course, we can not see much difference here than here. So in one sense, the motivation of tomography is that to obtain image of the slices of sections of the body, instead of just getting images of the projections of all the 3D volume, no, in a 2D image. What's the projection then? Radiographic images, or the ones that we have seen before, no, collapse the existing information in a volume of the two-dimensional image. Collapse existing information in a volume I think it's on the two-dimensional image. On the two-dimensional. Okay, a volume is concentrated, no, in a projection of 2D, in 2 dimensions. And that is the projection. Now, despite its usefulness, projected images have some disadvantages, like depth locality loss, no, propagation direction of radiation, and low contrast. Low contrast, we just mentioned that, right, in the previous image. And localization also is important because maybe here where the region where the mass, no, the malignant mass was. But even if there was some more contrast, like maybe the region that looks white, no, than the rest, even if we can more or less guess, no, where was especially that mass, this region, malignant region, we cannot see it was, no, at the beginning, at the end, no, of the brain, no, in which part of the brain. No? We only know that it was in that direction, but we cannot get this depth, no? Depth locality information. Because again, it's just a projection. It doesn't matter if it was before or after, no? At the beginning of the brain, or at the end of the brain. No? It's just everything is concentrated, no, in that direction. Okay. Okay, here we will start talking about this domain, no, of the radon transform that we were mentioning. The domain DZ. Okay, so now let's think about this structure. It's an object in 2 dimensions, an image. That could be a section of the body. So let's imagine that to the image. The image is located in a coordinate system, no? XY. Okay, and so until there, the intensity of the image, no, is determined by this function fxy, depending on the position. For this point, for example, there will be some intensity. For this position, there will be different intensity. Every point we have different intensity. Oh, we have some intensity. That intensity could be the same, no, for all the region. Outside, for example, how much is the intensity in this point, for example? How much is fxy? In this case, 0. No? If there is no information there or there's nothing there, fxy is 0. No? But for this point, or this point, some value. This value doesn't need to be like a constant C, no? Or some constant. It doesn't necessarily need to be one for all of them. It could be like maybe some region around here that has more intensity, more fxy, or different values. Okay, so we have xy, we have fxy. Where the projection thing comes from. Okay, so first we need to think about the projection not only from one source of X-ray, but many sources of X-ray. For example, let's say that we have first this source, the output of a tube, X-ray tube. And imagine that it's very a narrow beam, a narrow beam that goes in this direction only. Okay, so it goes in this direction, and at the end of that, we have some optical detector or some digital detector, some detector of X-ray. We will have some information here. If this, if between this source and this detector, there was part of the object. That object will attenuate, right? Will attenuate the X-ray intensity from the source. And then this X-ray tube is moved. The source is moved one distance or some distance to the next position, and the process is repeated. This source will send X-ray in this direction, and in this case, we cross all these. This detector that maybe this one doesn't move, or maybe we can have an array of detectors here. We detect something. We detect some information here. And if you compare the intensity, assuming that the intensity in the source was always the same, which detector will have more intensity? Of course, these two intensities detected here will be less than here, right? Will be less than here because the medium attenuates. And graphically, we can see that this distance is longer distance. So assuming that the attenuation is the same, around this region that around this region, this ray, X-ray in this direction attenuated more. So the intensity here should be less than here. Okay? And then we repeat that for this line. And then this detector will detect some how much was attenuation along this direction. Okay? And we repeat that for many of these sources. That's why it's parallel rays. It will look like parallel rays. And the first question we could be, okay, we have a 2D image that will be projected by this setup of X-ray source and X-ray detector. The projection here will be how? Will be in this domain, in this line, and will look only like a line. It will look like a line with some different intensities. Depending on the location, we will have more or less intensity. For example, I think the one that is here draws more area of the object, and probably will attenuate more. So the attenuation here will be much more than here. Or the intensity will be less here than here. So it's common here to use a graph or a plot of kind of attenuation attenuation depends in this coordinate P. Because this is, P is like the coordinates in this direction. Okay? In this direction. So we can say, for example, let's say that these 6 points are around here. So if you see here, where was more attenuation? More attenuation occurred around this circle. So attenuation really was around here. No, total attenuation. Total attenuation goes by this line, for this object in this direction. And in this point and this point, there was maybe only little attenuation around here. And this or this or this, there were maybe less and less. So you can create a signal, some signal that has this form. And maybe outside, if we can continue the detector here, the ray will not cross the object. So it's like there is no attenuation in that part. So we can, okay, if we continue this, it just means that the rest is just zero. Okay, and in a sense, this object that has some attenuation given by fxy is transformed, or it's converted in this projection, or this one-dimension line, this one-dimension function. This is called G of P. Okay. So basically, the projection that, in this case of the X-ray, converts a 3D volume in 2D image. What happens if we do this in a 2D image only, in a slice? We create only like one-dimension function. That one-dimension function looks like this. Okay, and this given by the function G of P. Why P corresponds? Okay, how much is, or what is this distance? Okay, the projection maybe is this part. If we look at this at the center of this point, for example, could be P equals 0. P equals 0, okay, so we will have some plot in one dimension. Okay, this function is given by this configuration, where there is some aspect most important, is this angle, the angle theta. When we had a projection in this direction such that the angle between P and X was theta, we have this function. So this function was really not only Gp but Gp theta, because it depends on the angle theta. If we then change the projection angle theta, this theta looks like 45 degrees approximately. What's happening is maybe we put the sources around here, around this line, and the detectors around this line, and make the angle theta equal 0 degrees, for example. So basically, P will be in this axis, parallel with X, so basically the same as X. In that case, how would look the function of Gp theta? It's basically, again, repeat the process of sending parallel rays. And we will see, okay, here the attenuation is nothing, but there is nothing there, nothing between this source and this detector. For this detector, well, there will be some attenuation given by this distance, so a little bit of attenuation. For this line, all this will contribute to the attenuation, so maybe something like this. And for this line, even more contribute to that. Maybe a little bit less around here. And for the last part, almost nothing. So it will be almost. And for this, around here. Okay, so this 1D dimension will be G of P and theta, but theta in particular with 0 degree. So there will be many types of projections depending on the angle, many possibilities. But all of them will look like a function. Will look like a function like this. Do you think that this 1D function is the same as this? Or we change with the angle? It will change with the angle, right? Because the projection, for example, in this very simple example, we are saying that it's proportional to this length. Because the attenuation, remember, it was E minus UL, right? Basically, the attenuation here was proportional to the length. So, different angles, we have different crossing lengths. So that will make that these functions are not the same. Depending, it will depend on GP and the angle. Okay. Now imagine that you have these 1D functions, these 1D functions, not for only theta 45 degree, like it looks here, or 0 degree, but for all the possible angles between 0 and 360 degrees. That is all the circle, all the circumference, all the coverage. We can have many of these curves. And basically, putting together all these GP functions, maybe plot this in two axes such that one axis has, for example, P values, and the other has theta values. All these amplitudes here can be basically intensity. For example, for the theta 45 degree, and P equal around this point, we have some pixels here, and this value will be what? Maybe it will be this value for 45 degrees, this amplitude. Let's say, for example, where would be this value? This value would be, it's for theta equal 0 degrees, and a P approximately greater than 0. So maybe 0 degree will be here, and here a little bit greater than 0 will be here. So maybe here we have the intensity of this pixel. So this amplitude, this value will be here as a pixel information, not an amplitude of the pixel. So basically, having all these points of the projection dp theta for all the possible angles will make that we can fill all the pixels of this p theta domain.
Profe,
Yes.
Cuando damos la vuelta, por ejemplo, el ángulo es 0, está de acá los sectores, y luego se da la vuelta a 180.
180.
La intensidad, o sea, la grafiquita sería lo mismo.
Very good question. No? If we do that from 0 degree and 180 degree, it's basically having the sources not here but here, right? The sources here and the detectors here. The lines that it crosses is about the same, right? It's about the same. And yeah, there should be some symmetry. There should be some symmetry between an angle theta and an angle theta plus 180 degrees. There should be a similarity. I think only in this case, what would be the difference? I think, for example, in this case, P larger than 0, P larger than 0 will be this point. But if we look the other way, when we are theta equal 180 degrees, and the sources are here, if we send this rays in this direction, the axis T will be kind of pointing this way. Right? So pointing in this way will make that this longer part is in a negative value of P instead of positive. But it's just like a small, very small difference. Something here. So it's like a G P theta, I think it will be like a G minus P theta plus 180 degrees. Something like that. Okay. Yeah, so in principle, this could be a one interpretation of the Radon transform. The Radon transform will be a group of pixels with information of the attenuation across some position and some angle theta. And that's for all possible values of theta and all possible values of position. Okay? The other, okay, that could be one definition of the Radon transform, and one way to interpret this. But probably the most important part of that is that knowing this information of all the pixels in the Radon transform domain would be enough to obtain back the image. We will see one or two examples of how the Radon transform looks, and it looks very ugly. It looks like that, nothing like the object. Okay, it's very difficult to interpret the Radon transform image in terms of P and theta. But even if it's difficult to interpret, we will see that it's possible to recover. Okay. Okay, so the relation between x, y, and p, t coordinate system is given by, and what is t here? Remember, x-axis, y-axis. This could be p with an angle theta, and this could be, or this is the axis t, okay, perpendicular to p. For this angle theta. So first there is like for example, an object like this. So if we have the projections in this direction, for example, for us it's important, for example, for this value of p, how is the length of all this across this path, this direction. Okay. Okay. So let's think that there is some coordinate here of x, y. Can you notice that this is x, y? It means that here is x and here is y. So the first thing is that x equal p cosine theta minus t sine theta, and y is p sine theta plus for some particular coordinate, like this. Can you see that this is true? Maybe you remember, right, when you did DSP, right, course, image transformations, some rotation. The rotation transformation, for example, was one possible transformation, and that was associated with cosine, minus sine, sine, cosine. This is familiar for any of you or not? Or you never seen this kind of transformation? This is very important, I think, because if you never seen this, you need to start reading, because this is like a basic, basic knowledge. Okay. A projection then is defined. The amplitude of the projection is defined as the integral of the function xy alongside the parallel trajectories to the direction of t. It's like how much is going to be the value of GP theta. We were mentioning that, okay, how much is going to be the value of GP theta corresponding to this value of p. Okay, that value will be this, right? The length of the function fxy, across this position. Even it's not only the length, but it's a little bit more complicated. That in fact it's there. It's like I will write it here. It's the integral of the function along dt. It's basically the amplitude here will be the integral fxy in the direction t, in this direction. Basically, the integral of the function in this direction. If this was a unique amplitude, like all the pixels here with the same amplitude, that integral would be basically the length of this function. Okay, it's a constant, so we just integrate t, we integrate t dt, and we just need to see only the limits of t. This point and this point. And basically the integral will be just length. This minus this. But if the amplitude was not constant, it doesn't matter. It means that the expression will be the integral of fxy. No? Well, this makes sense, right? It's just a projection. And then we can just write this maybe in terms of not xy, but in terms of t. So we write the integral. Fxy will be f of x, but x is p cosine theta minus t sin theta. And y is t sin theta plus t cosine theta. And the integral is still the differential term still there. Any questions? So this expression looks complicated, but it's not, right? It's really very simple. In fact, it's the integral of fxy, and maybe it's replacing the rotation, knowing the rotation of the axis. Right? When you go from the plane xy to plane p theta or pt. Then there is another form, another definition, if you want, of the Fourier, the Laurent transform. That is the second. I will write it. This is the second definition of the Laurent transform. No, sir. Well, it's dp theta for some value of t and some value of theta will be the double integral of the function multiplied by this delta function, and then differentiate dx dy. Maybe I will write it one more time. No? The differential of x cosine theta plus 1 sin theta plus 1 x y sin theta minus b. It's like, in fact, this is very similar expression. No? It's saying that, okay, you need to sum all the values of fxy in this line. And that line basically, for all these x, y values, we have this expression. No, this not only for this pixel, but it's really for all the pixels in this line. We'll call this. Let's call this value of p sub 0, okay, to make it more specific. So all the values x, y that have this form with p equal p sub 0 will be there. And from here, we can find that this you can multiply x cosine theta in both sides. And then sum this, so you will have x cosine theta plus y sine theta equal p sub 0 cosine squared plus sine squared, that is 1, right? 1, and these terms are cancelled, so we just have that. If I say all the points in this line should call this expression, should be such that, we can call theta 0, no? Some particular theta. All the points that call this, no? X cosine theta sub 0 plus y sine theta sub 0 equal p sub 0, all the values are here. For example, this pixel here, this is not true. Okay? For this pixel, if you replace whatever is the value x, y here, this is not true. But for some pixels here, it's true. Okay? So basically, this sum all the values of x, y, such that we multiply by this delta function. Delta function is like 1 when this is true, x cosine theta plus 1 sine theta minus b is equal to 0. When 0, 1. When it's different from 0, this is 0. So basically here we are saying that if it's true that x cosine theta plus y sine theta is equal to p, we can sum all the x, y values around this. So these two definitions are very similar. And sometimes we will use maybe this definition, sometimes we will use this definition, depending on the problem, depending on the case. Yeah, basically, the set of all the projections of an object is known as a random transform. Okay. ¿Cuál? Para este. O sea, este píxel no va a contribuir con la información en este punto P, ¿no? En este punto P sub 0. Pero sí contribuirá, por ejemplo, ¿no? Cuando P sub 0 es esto.
Claro, pero eso tendría que volver a calcular
Claro,
la línea para
tendría que volver a calcular aquí. De hecho, el cálculo, ¿no? Es ¿no? Para todas las líneas posibles se calcula. O sea, esta de aquí, esta integral, se hace para todos los valores P y Z, ¿no? Aquí le voy a poner P sub 0, T sub 0, ¿no? Cuando, por ejemplo, vale el valor de esta gráfica, P sub 0, T sub 0, pues será esto con T sub 0 con P sub 0. Con lo que estoy mostrando aquí.
Bueno, ese píxel sería un nuevo P1, por ejemplo, ¿no?
Exacto, exacto. Sería un G P1, por ejemplo, T sub 0. Y eso me va a dar el valor justamente, ¿no? En P1 T sub 0 de, en este caso, toda esta proyección. Esta función es bidimensional también, ¿no? Vale para todos los valores de P y para todos los valores de θ que podamos calcular.
Solo que no va a cambiar es el Z.
En este caso no, ¿no? Pero sí va a cambiar cuando, por ejemplo, el ángulo sea así, ¿no? Y la proyección sea en esta dirección. Entonces, hay muchas proyecciones involucradas, ¿no? Al final, cada una tendrá una expresión de este estilo, ¿no? Y se puede calcular con esta integral doble o con esta integral simple o integral